This video is in section 9.5, and we're going to be talking about example 6, finding the force required to hold a wagon on a hill. The question states, a wagon with two small children as occupants weighs 100 pounds and is on a hill with a grade of 20 degrees. What is the magnitude of the force that is required to keep the wagon from rolling down the hill? I'm now at the top of page 628. And at the top of 628, there's a lot of stuff going on. I'd like us to walk through it piece by piece. So they do give us a drawing. And then they tell us in this drawing we need to find the magnitude of the force, vector V, that would cause the wagon to roll down the hill. A force with the same magnitude in the opposite direction of when we find vector V is going to keep the wagon from rolling down the hill. The force of gravity is orthogonal to the level ground, so the force of the wagon due to gravity can be represented by. And so this might be something you write down as a trick, as an idea, as a direction on how to solve some of our vector word problems. So the force from gravity, it is written like this. I wrote this up on the side because it does not have the horizontal. It only has the vertical component. But this number, this 0 in a minute, is going to be important when we go to do a calculation. Determine the vector projection of the vector F from gravity onto vector W, which is the force parallel to the hill. So right here you see vector W. Vector V is the one we're talking about. Negative direction, the direction going down the hill is going to be a negative magnitude. But what we need is the positive magnitude to keep this wagon stationary. When it asks us to do the vector projection of vector F of gravity onto vector W, I'm going to go back over to, where did I want to go? Right here. I wanted to go back to page 627. And I know I ran through this in an earlier video, but I want to back up just a little bit. I had asked you to write specifically these two formulas on your formula card. I'd now like you to add a little bit to that to make sure we see these words vector projection of vector V onto W. And you might want to write it exactly like that. The vector projection of a vector, any kind, onto vector W, any kind, but notice the order. And then notice what it looks like in the formula. Sorry, I'm jumping down here because I asked you to write these two down. But notice they're going to talk about the vector projection for this one, which is this one. I've already asked you to write these on your notes, and so you might add a little extra note to this vector V sub 1. It is the vector projection of V onto W. And if it's V onto W, notice that V gets mentioned once, and vector W goes in the remaining spots. Vector projection of one vector onto another, the one that is written first, which is onto the other, that vector V goes down once, and vector W goes into all of the other three parts. So having said that, they are saying that we need to determine the vector projection of this force vector from gravity onto W, which is the one that we are looking for, which is the force parallel to the hill. W is given as, okay, whoa. A while back, we looked at various and sundry ways to write vectors. And with this one, since we have the angle, we're going to involve the vector form that has cosine and sine. So we now have our force vector related to gravity, and we have our vector that's going to be parallel to the one that we are talking about, vector V. The vector projection of this F onto W, F onto W. So I've got it covered up. But what we saw on the other page is F is going to get written once, and then W is going to go down in the rest of them. So the vector projection is going to be F written once. We're doing the dot product with it and W. It's going to be written there, and there, and there. Then we're going to need to find the magnitude of W and square it, and then multiply the whole thing times the magnitude of W. And so as they work through this negative 100, this first part is the dot product. And the dot product, you will recall, is taking the first parts, the horizontal parts, So this cosine 20 and this 0, which is not written over here, this is the horizontal, this is the vertical. So I'm going to take these two and multiply them. Well, when I multiply them, they're 0. So they didn't even write them down. We're supposed to add it to the the vertical parts. I hope I didn't say that wrong. We have multiplied the horizontal parts. They became 0. They did not even choose to write them down. If we want to go ahead and write it there, they became 0. Then we're supposed to add in the two vertical parts multiplied together, which are the negative 100 and sine of 20, which instead of saying add, we can go ahead and just say minus these two. Divided by, we need to divide it by the magnitude of W. You have that written on your formula card. The magnitude of W is going to be the square root of the first component squared, that's this cosine squared, plus the second component squared, that's the sine squared. And then when we get all of that done, we're supposed to take it, and according to the formula, square it. We still need to multiply in all of W. W is all of this, and so all of our vector W gets written in. What in the world are we doing? Where are we? What is going on? And ultimately, we are looking for, and I don't see it right here, we need to find the magnitude. The magnitude. In a formula a long time ago, not in a faraway galaxy, but a long time ago, we had a formula for V. And the front part is the magnitude of V multiplied by other stuff with sine and cosine. Here it is. That's the number we're looking for. And so when we come back over here to what we have, here's this back part, which is the magnitude of W. It's going to be this leftover part for what we're looking for. So what I'm going to do is I'm going to take a calculator here, and I'm going to multiply all of this, divide all of this, square root it, square, punch it in, blah, blah, blah. And when I punch all of this in, and it's going to depend on my calculator how I do that, and I have to do it very carefully. I might need to throw in extra parentheses. It's just going to depend on your calculator. But I just punched it in on my TI 30X2S, and I got the same as they got. I got the negative 32 and 2/10. All of this mess times this back end. I want to point out again on page 616, here's the form for our vector. Magnitude times the rest of the stuff. And so it says up here we need to find the magnitude of V. V is actually going to be negative, and looky there. Our magnitude of V is right here. That's the number we want, but not really. We want the magnitude of V, but earlier we talked about it's going to be taking us downhill. We need the opposite of that to be able to make this not go downhill. So in summary, the magnitude of V is going to be 34. The magnitude of the force required to keep the wagon from falling down the hill is going to be this 34 and 2/10 pounds. We made it. That ends example 6 in lesson 9.5.